comes from a certain direction and has some temporal statistics, and also the noise may come from different directions. And the model is that for each microphone or each sensor M, it's just like also with image processing, joint deblurring, and noise reduction. And other methods also. Other water acoustics also. You have some ways to do that. Because over there, it's even more important to deal with this impulse responses. Okay? So this vector is x1t, x1t minus 1, and so on. And generally, we can choose how many samples we choose. But let's take a vector of length L. So this vector, we can obtain it from some measurements that we get from the sensors and from all the sensors. So we combine L sensors from each, L samples from each sensor, and we concatenate them into a long vector of length ML. So we have a vector T of length ML by 1. So this is the vector. It contains L samples from each sensor concatenated over all the sensors. So here, what we try to get is to find a matrix, filtering matrix, and the size will be L by ML, which is multiplied with the vector T of length ML. So we combine, so all this is linear model and linear estimation. And then we define also the performance measures. Okay, so performance measures, we talked about output SNR, input SNR, we talked about distortion, noise reduction, desired signal reduction factor, and we talked also about the mean squared error. So the mean squared error means, you see that when you estimate something like that, we have two components. One is what is, because also here, this vector, we can write it as a summation of two vectors of the desired signal. This is the desired signal that is measured in all the sensors, L samples, and concatenated over all the M's and 1. So we have ML sample. What is, because also here, this vector, we can write it as a summation of ML samples of the desired signal. Of course, it is not the desired signal, one of them, but we assume in all the that we know the correlation between any sample in this vector all the M samples in this vector. So we have ML, the L what is, because we know here in this vector, any sample, write it from any sensor, L sample, and find the correlation of any sample, it is not the desired signal, one of them, with the same, any other correlation between concatenated samples over all the M samples. We call it, so we have ML, what is, because we know here the same sample, write it from the base, RV. And we gave some examples. We gave some examples how to obtain these matrices. In practice, you need to estimate them. So if you read, for example, some papers, you can check my website, you can find the papers, and also about practical problems of, for example, speech enhancement and array processing, how to estimate something like that. Okay? And I hope that when you present your topics, you can talk about things that you're familiar with, what are the challenges, and so on. So you don't have reliable information and you need to estimate. And then it's more challenging. Okay, so if we have this, we can define what is the mean squared error, for example, mean squared error, and we can define it as a function of h, and try to find h that minimizes this mean squared error. In this matrix, we will call it Wiener filtering matrix because it minimizes the mean squared error. But instead of working directly with the matrix H and these matrices, we said, let's transform the signals into the generalized, using the generalized eigenvectors of these two. Okay, so what we did, okay, I can write it here. So what we did, we said, let's find the generalized eigenvectors and generalized eigenvalues of these two matrices. So we know that these two matrices are symmetric, and also they are full rank. So we can find the matrix T and diagonal matrix lambda such that T transpose Rx T equals to lambda. Lambda on the diagonal contains the eigenvalues in a decreasing order, and the columns of T are the generalized eigenvectors, and also the same time T transpose RV T equals to identity matrix of size ML by ML. Okay. So we can find, we know how to find these matrix and these generalized eigenvalues. Once we found it, it's much easier to work with filtering matrices, to find optimal filtering matrices. So instead of writing J as a function of H, we can write H by A, T transpose. So now we formulate, instead of formulating the performance measures as a function of H, we can formulate them as a function of A in the transform domain because T is known. And once we find the optimal A, we can find the optimal H simply by multiplying with T transpose. Okay? So if we find from the problem J as a function of A, we can find the derivative of this, a scalar function. We find the derivative, the gradient, with respect to the matrix A, equate it to 0, and find the optimal A that minimizes the mean squared error. And then we multiply it with the T transpose, and we get the Wiener filtering matrix. And it's easier to work also, as we will see, also to find the MVDR and other methods. And we saw that we can write, of course, you can write H, the Wiener filtering matrix. You obtain it in a certain way. You can write H, Wiener. So we saw that, let's see, okay. For the example. Okay, so you can write it directly without using transform, this generalized eigenvalue decomposition. And you can find it like this. And also I gave you the definition of II. II is identity matrix, and all the other and below are zero. So you can check the definition. So we can write it as II, this is a matrix, multiply with Rx, Ry minus 1. Of course, we can obtain it like this. But if we use the transform domain and we find A, the optimal A that minimizes the MSE, and then we multiply with the matrix T transpose from the right, we get another formulation of the Wiener filtering matrices, which looks like that, which is a nice way to get this one. See, this one. So we got it as I Rx summation from I equals to 1 to ML, and Ti, which is the column, the I column in the matrix T, Ti transpose divided by 1 plus lambda I. Lambda I is the ith element in this matrix lambda along the diagonal, which is the eigenvalue in a decreasing order. Okay, so this formulation is really nice because it enables us to take a smaller number in the summation here. We don't need to take all the elements in the summation. We can take smaller number. And also, another nice thing is that we don't need to compute the inverse of a large matrix. You see, this matrix is ML by ML. Here, we don't need to compute the inverse of this of a matrix. Sometimes it's helpful because it saves computational complexity. But of course, the computational complexity, we have it here with finding the transform. But here, so in addition to not, we don't need to find the inverse of a large matrix, and we write it here, it enables us to control the trade-off between signal distortion and noise reduction by changing the number, how many elements we sum in this expression. And then we said that if we reduce, so here we, instead of taking the summation overall until ML, we can take some summation with a smaller number, let's say Q. So we call it a different filtering matrix, which we call it variable span. Okay? So we call it variable span Wiener filtering. Okay, all this I can delete. So from this expression, we found an alternative way to do, to add some, you see with the Wiener filtering matrix, we don't have a trade-off to control the signal distortion and the noise reduction. We don't have, because we just minimize the mean squared error. So this minimizes the mean squared error. But if we define another matrix that with a parameter Q that looks like that, summation from I equals to 1 to Q, and Q is generally smaller than ML, then we can control the trade-off between noise reduction and signal distortion. Which is nice. And then we saw also an example how the choice of Q controls this trade-off. And you see, when we talk about trade-off between noise reduction and signal distortion, we always want to do it in a smart way. We don't suppress more noise if we want to suppress noise. First, we put to zero all the noise components in the noise subspace, okay? This is obvious, because then we don't pay for that. We don't pay for that with signal distortion. So always, when we have a signal subspace, we have a signal subspace, okay, and noise subspace, we remove all the components in the noise-only subspace. This is first thing with all filters, whatever you do. Now, in the signal plus noise subspace, we want to reduce noise. Of course, it will come with the cost of increasing the signal distortion. And the smart way is to reduce in such a way that you pay the least amount of distortion for noise reduction. So you want to reduce maximum noise with the least amount of distortion. And the nice thing is, okay, nice thing is that when you increase I, and you, okay, we need to prove it, okay? But I will talk about it, how to think about it. When you see a summation here, so the first term reserves the maximum amount of signal. The second term is the second, and so on. So if we remove the last term, it reduces noise with the least amount of distortion, and so on. So gradually, we remove the last terms, which is not obvious in this formulation. Why we can take that? Why do I have that? And you need to prove it. I didn't prove it here, but I want you to understand that when we find the generalized eigenvectors and generalized eigenvalues along the diagonal here, so lambda I is in a decreasing order, okay? And what I claim is that once you order the generalized eigenvector, generalized eigenvalues in a decreasing orders of lambda, the first term and the second term and the third term, so it goes like the significance of the last terms are less important than the first terms. So it's in a decreasing order of importance regarding the signal distortion. So once we remove the last terms here, we're able to suppress noise with the least amount of signal distortion. Okay? So we want to show, we can show that when we increase Q, Q to Q plus 1, we have less distortion. Okay? That's why we want to remove the last terms when we want to reduce noise. Of course, you could ask why to start from I1 to ML. Maybe we can start from the second, from the third, so on. But this doesn't make sense, because then when you reduce noise, you want to produce the least amount of distortion. So when I talk or mention or try to find something, a variable, like here, a variable Q, that will give me a control between signal distortion and noise reduction, I need to do it in a smart way, such that I get the maximum amount of noise reduction with the least amount of distortion. Otherwise, this variable is not a good way to control this trade-off. When I talk about trade-off, I mean optimal way to control the trade-off. This is important. Just like we mentioned that in the single channel signal enhancement, in the time domain, in the frequency domain, when we add mu over there with the trade-off, so that was a way to do it, and so on. So you need, when you provide some variables to control something, here in our problem is to control distortion and noise reduction. But if you, in your research, you try to control some trade-off, you need to prove that this is the best way to control the trade-off using a certain formulation. I don't say that this is the only way to control the trade-off. Of course not. We will see other ways to control the trade-offs. But once you use a certain parameter, you see, maybe I need to choose the first one, the fifth one, and the element number 19. Maybe it's better than choosing, suppose that I want to choose 5 elements of this summation, only 5 elements out of ML elements. So what I say, using this formulation in this generalized eigenvalue decomposition, I tell you, if you want to take summation of only 5 elements, take the first 5. And you need to prove that the first 5 are better than taking any other 5 elements. Okay? Any questions so far? Okay, so we talked about the variable span Wiener filtering matrix. We also showed some examples, and we saw that if we take the first element, actually, it generates a way to maximize the output SNR. So if we take only the first element, which looks like that, T1, okay? So if we take only the first element in this summation, we get a filtering matrix that obtains maximum output SNR. And of course, we have other solutions to obtain other filtering matrices to obtain the maximum SNR. So we can put number 1, so this is one of the options, like this, which is nice. You see, so from this formulation, we obtained also variable span, so we can control the trade-off between signal distortion and noise reduction. And we can also get easily, by taking only the first term, filtering matrix that maximizes the signal to noise ratio. And we can show also, we can prove mathematically that this filtering matrix, it maximizes the SNR together with minimizing the mean squared error. So if we take out of all the filtering matrices that maximize the output signal to noise ratio, and we want out of all these filtering matrices to find the one that minimizes the mean squared error, it will be this one. And it was obtained from the first term in the sum of the Wiener filtering matrix. By the way, I gave you, shared with you the book chapters. At the end of each chapter, there are many problems. So if you like, if you have more time and you want to prove everything, so you can prove, you can just follow the problems at the end of each chapter and try to prove things. So it's a good exercise. So many things that I say, I don't give you the proof, but you can prove it, so it's in the book. Okay? Any questions? Okay, good. Now we can move on to the MVDR. Okay, so the MVDR, what does it do? The MVDR, if we go to this transform domain, we know that the components of the signal are spanned by some P eigenvectors, generalized eigenvectors, because the dimension of Rx, the rank of Rx is P. Smaller is a lower rank. So if we keep these eigenvectors, the projection on this signal subspace, we don't touch it. We don't reduce any noise in the noise plus noise subspace. We remove only the noise in the noise only subspace. We get MVDR. It's very nice. So how do we do it mathematically? Once we do it in the transform domain, it's much easier because we can separate. We can have an optimal separation between the signal subspace and the noise subspace. What does it mean, optimal separation? It means that the signal or the dimension of the noise-only subspace is the largest because we have the least number of eigenvectors or basis functions that span the signal subspace. So the signal subspace is the most concentrated in that transform. Once we have such a transform that we can concentrate all the signal components into the smaller dimension of the subspace, we can have good separation between them, and then the MVDR will be able to suppress as much as possible noise without any distortion to the desired signal. Okay? Makes sense. That's why we work in this transform domain. You can ask, is there any other transform? But we can show that this is the optimal. Sometimes we don't work with such kind of transform because it's expensive. It's expensive computationally to find these generalized eigenvectors and generalized eigenvalues, but then you can do something which approximate or come closer. For example, with speech, you can choose the short-time Fourier transform. With images, you can do something else. Sometimes we work with the two-dimensional DCT and so on. But then you can do offline some computation, and you can ask how much performance we lose because we didn't use the optimal subspace transform, the optimal transform like this, and we used an approximate alternative transform like the STFT or the 2D DCT for images or some other transform. And we want to know how much we lose, how much the performance degrades. This is a good question, and we can test it on real signals. Okay? So if we don't adapt the transform to the signals, we can obtain lower computational complexity, which is very important. And then we can compare it to the best transform and see how much we lose in terms of performance. So for the MVDR, we need to find the optimal A such that we get maximum noise reduction without any distortion. So how do we do that? We need to find the matrix A such that when we apply, so I delete it over there, but we need to show that when we apply H, which is A, T, T transpose, okay? When we apply H to X, okay? If we apply, this is the filter desired. This is a vector of ML by 1, okay? This is ML by 1. This is the filtering matrix, which is L by ML. So we need to show that this is the filter desired signal. We need to show that this will be X1, which is L by 1. This will obtain or will generate the first L samples or the L samples in the reference sensor. If we have this, do you agree that we have distortionless response? Yes, good. Because Z, okay, I need to add here T, just notation. Because ZT, which is an estimate of X1, is H Y. So if we apply H to X, Y is so if we apply H to X, we want to get exactly the original signal without any distortion. Of course, we will pay for that by removing less noise. But so we remove only the noise in the noise-only space. So if we write it like this, we can write it also in the transform domain using the matrix A. Because H is A T transpose. So in the transform domain, we work with the matrix, the filtering matrix A in the transform domain, and we show that this requirement, the distortionless requirement, is the same as this. You see? A lambda is II Rx T. And you could put, you can first, there are different ways to find it. Either you find it from here, or you take the MSC that is based on the distortion MSC, distortion-based MSC, JDA. You minimize it, and so you find the gradient of this and equate it to 0, you find this. And once you use it, you need to show that actually the MSC of the distortion will be 0. But you can also find it from here. Okay, so you can practice, try to solve it. And from here, because lambda is diagonal, lambda contains the generalized eigenvalue. So it's very easy to invert it like this. But you know that lambda contains p eigenvalues, which are larger than 0, and the others are 0. So you cannot just take lambda minus 1, it's non-diagonal. But if you take a diagonal matrix with some 0 elements, it's very easy to invert it. We call it pseudo-inverse, okay? So pseudo-inverse, it means that you invert, you take the inverse in the diagonal of the non-zero element, and you keep the 0 element in the same place without touching them. Sometimes, even the small eigenvalues, you see, the small eigenvalues, sometimes we put them to 0 because this becomes large value, but this will create some distortion. So here we take all the non-negative eigenvalues, we invert them, and this is a pseudo-inverse of diagonal matrix, which is very easy to do. See? So this is the matrix of the MVDR. If we multiply with T transform, we get the MVDR filtering matrix, which looks like that. So here we get a nice formulation for the MVDR, which looks like, you see, also we have summation. But instead of 1 plus lambda, what do we have here? Lambda. So first, it's very nice to see the equivalence between here, this expression, and the Wiener filtering matrix. Two differences. First, here, instead of 1 plus lambda, we have lambda. It's okay? The second thing is that summation goes to P. We don't need to go to ML, only to P. So we take this summation only over the first P element of the generalized eigenvectors and the generalized eigenvalues. So this expression gives us exactly distortionless response. So the desired signal is undistorted, and we suppress all the elements that contribute to noise in the estimate. We remove all the noise in the noise-only subspace. So let's write it. HMVDR. So it's IRX summation I from 1 to P TI transpose divided by lambda. Now we can ask ourselves, we have an expression for the MVDR. Now suppose that we want to enable some distortion in order to reduce more noise. The MVDR reduces the maximum of noise without any distortion. Now suppose that I want to reduce more noise, additional noise, and to pay with some distortion. But I want to pay with the least amount of distortion. Which element out of this summation I will get rid of? The first one, the second one, third, or the last one? Okay? The last one, okay? So because the eigenvalues, the generalized eigenvalues, are ordered in our transform by decreasing order, so the last one, if I remove the last one, the distortion will be minimal. And then, so these elements are ordered according to decreasing order of distortion. What will they create if I remove them? So if I want to remove some amount of noise with the least amount of distortion, I will take this summation from I equals to 1 to P prime, and P prime can be smaller than P. TI transpose lambda I. Very nice. So we have another way to control between speech distortion and noise reduction using this parameter, P prime. So we can call this something. You can choose a name, okay? But we can choose a name, so we can call it H control distortion, okay? But any name is fine with the parameter P prime. So this filtering matrix enables us to control in a smart way between noise reduction and speech distortion or signal distortion by using a parameter. And you see, it's in a smart way because it's easy to control using the parameter. We just take the summation until some components, because these components are ordered in the best way according to decreasing order of the trade-off between noise reduction and signal distortion. It's beautiful, you see, because sometimes you think, okay, suppose that I need to remove some components, I need to find it. Here you don't need to find it. It's already in order of importance. Also here, it's in the order of importance that allows us to do some smart control over the trade-off. Now, if I choose only the first component, it means that it will keep only one component of the signal in the best way, where the signal is the most concentrated in that component. And actually, it will reduce also maximum SNR. I can show that even the first component, if I use it, I get maximum SNR filtering matrix. How do I know that? Because if I use it, the output SNR will be the maximum possible value, lambda 1. Okay? So you see, this is another expression for maximum SNR filtering matrix. So I call it number 2 because it's another. I want to identify this from this. Both of them, if you use them, the output SNR will be the maximum possible SNR. What about, so what is the difference between these two? If I have two different expressions that produce the maximum SNR, okay? What's the difference? So I said, sometimes I have an infinite number of filtering matrices that can generate the maximum SNR. So here it's the filtering matrix that produces the maximum SNR, but out of all the filtering matrices that obtain the maximum output SNR, I choose the one that minimizes the MSE. Here, out of all the matrices that obtain the maximum SNR, I choose the one with the minimum distortion, minimum signal distortion, which is different. Okay? Minimum distortion is this part becomes as close as possible to X1. What is MSE? That this part is as close as possible to X1 in the mean squared error sense. It's different. Okay? So we have here different expressions out of the infinite number of filtering matrices that obtain the maximum SNR. We have specific solutions that we got immediately from these expressions. You see the beauty of these derivations, and it allows us to do some more ways to control between signal distortion and noise reduction. You see, so if we have here a way to control between noise reduction and signal distortion, and here I have a way to control between signal distortion and noise reduction, which one is better? Which one is better way to control this trade-off? Okay? Is it a legitimate question? Always when you do research, ask questions, even if you don't know the answers. Research is to answer the questions, but the significant part of research is to ask questions. When you get something, ask questions. Be curious about what you get. Okay, so what do you think? Give me any answer. Intuitive, not intuitive, or think about an answer. Can be correct, incorrect, everything is good. What do you think? So which expression is a better way to control between noise reduction and signal distortion? Which expression is better? What? This one is better? The CD, the control distortion, is better than this one? Okay. Somebody think differently? Okay. So I think I gave you a clue when we talked about this. So I'll go backwards. Ask which one, this generates or obtains the maximum SNR. This obtains the maximum possible output SNR. Both obtain the maximum SNR. Which one is better? This one or this one? Both obtain the maximum SNR. Which one is better? If we have two expressions, two things that produce the same results in terms of output SNR, so what are the differences between them? What are the differences between these two? Both produce the maximum SNR. What are the differences? Exactly. One minimizes the mean squared error. One minimizes the distortion. Okay? So it means minimizing the MSE, it means that the difference between Z and X1 on the average, it will be minimal using this. But if I care only about the signal distortion, the error between this part and X1, it will be minimal using this. Okay? So I can ask more questions, but I don't want to add more questions. One question at a time. So which one is better? MSE or distortion? MSE is better than distortion? Okay. And also you think MSE or distortion? Distortion. You see? So two people think differently. But you are both right. Because it depends what you need. Because in some applications, the distortion is more important. So you will choose something that minimizes the distortion. In some applications, you don't care about distortion, you care about the error, the mean squared error. Okay? And then this expression is better. So with the maximum SNR filters, also in the time domain, frequency domain, what we showed in the time domain, also here in the multi-channel, maximum SNR. So you have many solutions. So you have a degree of freedom to choose which one you choose. So if you care more about the MSE, you will choose this. If you care more about distortion, you will choose this. So it's a flexible, see? Okay, and another question. Which one suppress more noise? Which one? This one, MSE, number one or number two? Both generate the maximum output SNR, okay? One of them minimizes the MSE out of these matrices. One of them minimizes the distortion, this part. Second one or first one, okay? Okay, why? Makes sense, okay? I agree, makes sense. The first one, the MSE, it minimizes the difference between this and X1, the MSE. So it's MSE-based maximum SNR filtering. So it means that it gives some importance or weight to both this and this, how they different from X1. So the residual noise is also important. Here, we care only on the distortion. So we want this to be as close as possible to X1, which means that we don't give any importance to the residual noise. So it will try, so this filtering matrix tries to minimize the error between the filter desired and X1, but it will pay. We'll pay for that by increasing the residual noise. Okay? So the part of the residual noise will be higher in using this compared to using Hmax-Y. Okay? So we have nice expressions, and then we can ask some questions and so on. We can continue with that. So you see, it's very beautiful when we work with some expressions, and we can also think. So when you take summation, you also get nice order of their importance. If you work in a with a different transform, it's not that obvious. But you can approximate, and you can try to find which elements to remove. But when we work with eigenvalue decomposition, just like we work with the time domain, or when in the multi-channel time domain we work with generalized eigenvalue decomposition, it gives us beautiful expressions that we can work very nicely and derive different filters in a straightforward way. Okay? But we need to understand what we get, because sometimes we get the mathematical expressions and we don't know how to interpret them. So it's important that we know how to handle them. Okay, so this is the MVDR. So actually what we got now is 3 more filtering matrices. MVDR, control distortion, and a filter that maximizes the SNR, maximum SNR filtering matrix that minimizes the distortion. Very nice. So actually, everything I already explained, so I can skip. I can skip the derivations. And the nice thing is that also the output SNR with MVDR is always larger than the input SNR. Okay? So even that you take all these components, you see the maximum SNR is obtained with the first component. With the first component. If you take P prime smaller and smaller and smaller, you increase the output SNR. So you increase the output SNR, you reduce more noise, but also you increase the noise reduction, you increase distortion. Okay? But even if you take all these components, of course, the output SNR is at least as the input SNR. When do we have equality? What do you think? Using this. When what? Rx is full rank, which means that P equals to ML. Very good answer. Good, good. Because then we don't have noise subspace. It's empty. We have only signal plus noise, so we cannot remove any noise using the MVDR if we don't have a noise-only subspace. Okay. The control distortion is taking the summation up to P prime, which is smaller than P. Okay, and then we can control and so on. Let's see an example. So, by the way, you told them that we continue until 10:30, okay? So we continue instead of 1 hour until 10:30 because today is Christmas, so the break will be at 10:30, okay? So I don't want them to rush and think, okay, well, maybe I forgot about the break. Don't worry, I'll give you a break at 10:30. Okay, so let's see an example. If we return to example number 2 that we talked before, actually, if I go back to the example, so it was yesterday, so maybe you don't remember. So this is the example, that we have a signal like this, xt prime. So we have a signal that we don't know the properties of the signal, but we know the correlation between any two samples in this signal. Actually, we have some signals like this, that the correlation between two samples decays by their distance, the distance between samples. The more distant they are, the correlation decreases. And alpha doesn't have to be a positive number. So sometimes we have correlation which is negative, which means that the sample changes sign from one sample to another. So the odd samples can be negative, the positive samples can be positive, but we have some correlation between the samples. So alpha can be even negative. But it has to be smaller than 1, so the correlation decreases. Okay? And we can find for this example, suppose that we have the signal, the desired signal that comes from, let's say in the example 2, I think it's over there from the broadside. And in this area, okay. And interference, and we have also thermal noise, and the interference comes from the end fire. So we can find the correlation matrix and correlation matrices of the desired signal, Rx, and the correlation matrix of the noise. And suppose that here we choose alpha to be 0.8, and we take L samples, 10 samples for each sensor, from each sensor, and we have 5 sensors. Okay? So this is the example that we showed with the variable span, and if we take the controlled distortion, so we have also some trade-off with the controlled distortion. You see, so if we compare the controlled distortion, first I want to describe what we get with the controlled distortion for the same example that we showed also before for the variable span. So with the variable span, we changed Q. With the controlled distortion, we change P prime. So P prime can be 1, 2, 3, or 4. Okay? 1, 2, 3, or 4. Okay? So when we take P prime to be larger, so we add here, we have here more components, so we reduce less noise. So the noise reduction factor decreases, and the signal to noise output SNR decreases. You see the maximum SNR is obtained with P equals to 1. And when the noise reduction decreases, also the distortion decreases. See, so by controlling P, we can control the trade-off between noise reduction and signal distortion. And the MSC also decreases when we increase P prime. So if we compare the MSC, you see, if we, okay, well, first question. If I compare here the output SNR here that is obtained with P equals to 1, or the output SNR that is obtained with Q equals to 1, which one will be higher here? Same example. If I compare the output, the gain in SNR as a function of input SNR, one for using the control distortion filtering matrix with P prime equals to 1, compared to the variable span that we had here, variable span, which is here, with Q equals to 1. Which one will generate higher gain in SNR? Okay, simple question. What? Q equals to 1? Let's compare. So here, the value here, 24.3 approximately. Let's go to the previous one with the variable span. Here. This is, let me see if it's the same. Okay, so alpha equals to 0.8, and L equals to 10, and M equals to 5. Let me check that the input SNR, so it depends also on the input SNR. As a function of the input SNR. Okay? So if you compare, so here it's 24.3 approximately. Over here, the same range of input SNR from -5 to 15 dB. 24.3 approximately. So it's hard to see, but so it looks similar, but it should be the same, right? So it's the same. Of course it's the same. So that was an easy question. Why is it the same? Exactly. So H max 1 and H max 2 both produce the same output SNR, the maximum SNR, lambda 1. So of course it's the same. But now let's compare the MSC. Which one produces lower MSC? Using the first one, this one or this one? Which one produces? The first one, okay? So let's check, because maybe something is wrong with the simulation, okay? So let's check. So here the MSC is about 9.5, slightly below 9.5. This is using the variable span, okay? Which is the first one, 9.5. Let's go to the controlled. So the MSC is here, okay? So maybe it's almost the same, but this is the first one, okay? So maybe the difference is so small that we don't see it, okay? If we go further, but if we increase P prime to 4, for example, so we get this value using 4 terms. So it's about 7 point, this is 8, so let's say 7.7. If we go to the previous one, see here, so it's 7 here with a variable span, Wiener. Okay, so it's much lower because with a variable span, we try to minimize the MSC. So if we take 4 components, actually here it's 9 components, so it's unfair. So here with the Q equals to 5, this is 5. So this is with 5 components. So we need to compare the same number of components, okay? So it's more fair. So let's take Q equals to 2 here. So it's 8.75, maybe. 8.75, well, maybe it will be similar. 8.75. So the MSC is quite similar. So you see in this example, it doesn't, even though here we try to minimize the MSC and here we try to minimize the distortion, the differences in terms of distortion with a small number of components is not necessarily big, okay? So maybe small differences. For this example, you see, because the distortion is, and so probably the noise reduction will be also something similar, but this is a different way to control how we control the distortion. Okay, Now let's talk about additional way to control distortion, which we are familiar with. When we try to minimize, we obtain the Wiener filtering matrix by minimizing the MSE. And we know that the MSE, J, A, the MSE, is composed of two components. One is related to the distortion, and one is related to the residual noise. So instead of minimizing their summation, we can put here a parameter, mu. So if mu larger than 1, we will have more noise reduction. And if mu is smaller than 1 compared to the Wiener filtering matrix, if mu is smaller than 1, we can have less noise reduction and less distortion. So it's also something that we are familiar because we studied that. This is a nice way, also an alternative way to control. So let's see how it looks like. So the trade-off filtering matrix, see, we try to minimize using a Lagrange multiplier, and we get this formula. So using this formula, how does it compare to the Wiener filtering matrix? Simply, instead of 1, we have here mu. So this is H, the trade-off filtering matrix. Okay? So this is trade-off filtering matrix, which is I, Rx, summation from I equals to 1 to ML Ti transpose divided by mu plus lambda I. So we say, okay, why should we control the trade-off between noise reduction and signal distortion using one parameter? Maybe we can choose both mu and also here Q. Okay? This is one question. So we can control using two parameters. Why to limit ourselves to a single parameter? Another thing is, what happens if I put here mu equals to 0? What does it mean? If mu equals to 0 and I try to minimize this, so I don't care about noise. I care about distortion. What do I get if mu equals to 0? MVDR. MVDR. And if I reduce the number of components, I get the control distortion. So all these connect. You see the relations between all these filtering methods. They're all connected when you have a combined representation of these filtering matrices. So what I can do, I can formulate, I'll return to this example shortly, but I now can formulate a more general filtering matrix. I will call it general subspace filtering matrix. It's just a name. You can call it any name. You give it an Indian name. Okay? It's also fine. Any name is fine. Makes sense. You can invent names for new things. Try to do it for new things. If you do it for something which is known, and you put a new name, so people think, okay, you're not familiar with what exists. You know, sometimes people find a star, a new star, and then they give it a name. Some people look for stars. They spend many hours to look for a star that was not named before, so they can give it a name. You know? So you can also do it in mathematics and signal processing. Okay, so suppose that you have this filtering matrix. You see we have two parameters, mu and q, that control the the trade-off between noise reduction and signal distortion. A very beautiful way to control the signal. But now we understand something which is very nice. We understand that if we take mu equal to 0, if mu is 0, we get a control by minimizing the distortion. We put more emphasis, because if we put mu equals to 0, we put more emphasis on the distortion. So we have control under the constraint or under the additional requirement of minimum signal distortion. If mu is larger than 1, so mu is larger than 0, okay? So it can be 0 or larger than 0. If we take mu, we increase mu, we give more emphasis here. So as we increase mu, we reduce more noise. And still, for a given mu, we can control the trade-off between noise reduction and signal distortion by choosing Q, which is smaller than ML. But if mu equals to 0, don't put here something which is larger than the dimension of the Rx. Okay, so the maximum Q can be P. Okay, so we write here Q between 1 and ML, but if this is for mu larger than 0. If mu is 0, the maximum value of Q will be P. And you understand why. Because we've gone through all of that. So we have many special cases of this general formulation. So we obtained a nice way to control signal distortion and noise reduction using two parameters, mu and Q. And we also understand each one what it does. So this we explored. Let's go to the example that we skipped with the trade-off. Just a minute. Okay, so this is the example. So we have the same example. So I just want to show the effect of mu. So here we have the gain in SNR, we have the MSE, we have the noise reduction factor, and the distortion, the desired signal reduction factor. For different values as a function of input SNR, for different values of mu. So you see, let's see here, the blue line is with mu equals to 0.5, the green mu equals to 1, red mu equals to 2, and then the last one, the light blue, cyan, is mu equals to 5. So you see for a given input SNR, when you increase mu, the noise reduction factor increases because we suppress more noise. We increase mu, we give more importance to this part, so the noise reduction increases. And then the output SNR increases because we increase the noise reduction. And the distortion also increases because we pay for that with the signal distortion. Here, the minimal MSE will be obtained when mu equals to 1, because mu equals to 1 minimizes the total mean squared error. That's why the green line obtains the minimal MSE. Any questions? Okay. So this is a nice way, we derived it. And here you have a very table that shows. So this is the general subspace with the parameters mu and Q. And all the others can be considered as special cases of this general formulation. Okay, the Wiener, variable span Wiener, MVDR, control distortion, maximum SNR. So we have two options. Okay, but we have actually more than two options. Any mu that we put here, so I showed here mu equals to 1, and here mu equals to 0. But actually, any mu will generate the maximum SNR. Okay, so you can choose any mu. How to choose mu? So actually, this expression gives you the maximum SNR filtering matrix. So we have, you see, you have an infinite number of filtering matrices that generate the, the, the maximum SNR. And then we can choose mu such that it will control the trade-off between noise reduction and signal distortion. Intuitively, think about, we have many signal components in the signal plus noise subspace. So with the maximum SNR filtering, we keep only one component. Which component do we choose? The one with the maximum SNR, okay? Exactly. So we keep that one. Now, if we multiply this component with a certain value, do we change the output SNR? No. We don't change the output SNR. Okay, so we multiply this component with any value. But we change, if we multiply it with a certain value, we change the MSC, we change the distortion, and we change the noise reduction, okay? So we can control what is the value that we multiply this component. Still, we get the maximum SNR, but this variable that we change, we multiply this component, will allow us the trade-off between noise reduction. So even with the maximum SNR, we can control the trade-off. So this is a way to choose the component with the highest SNR, and then we control how much we reduce noise compared to how much we introduce distortion in this component, okay? And we have the trade-off, more general, that we choose more elements. This is the general form. Any questions? Okay, so you have here some references. And now is exactly the time, almost 10:30. So I'll give you a break, and then we will continue. Now that you understand the single channel in the time domain, you saw that when we move to multi-channel in the time domain, it's such an extension of the problem formulation, the derivation, and so on. And we did some extension that was really nice. We found that the filtering matrices take into account the temporal correlation and also the spatial correlation in the vectors. So now, in the frequency domain, in the single channel, we used only gains for each frequency. We worked with each frequency independently, and we found the optimal gains. Now, when we go to or extend it to multi-channel signal enhancement in the frequency domain, we now will use the correlation between sensors in the frequencies. Okay, so if we have two different sensors, we will use the correlation between the frequency components of these two sensors. So we are able to do also spatial filtering in addition to filtering in the frequency domain. Okay? Questions? Okay, so we have a break. We will continue. When do we return? Actually, we have 1.5 hours now and 1.5 hours afterwards. So it's up to you. Maybe
These days, more companies are investing in autonomous vehicles. From ride-sharing services like Uber to large auto manufacturers like Audi, the industry is booming. Despite growing interest, the technology itself is in a proof of concept testing stage. It's smart, but engineers are working to make it smarter. Turning a manually operated car into an automated one requires data to be acquired and processed the same way humans innately do. Every day, we interact with the environment through sight, sound, and touch. To drive a vehicle, we are also guided by backup cameras and side and rearview mirrors, and by sensors that monitor road conditions and activate our brakes accordingly. The human gives all the gathered data to the brain to process this information and make decisions. Cars must have sensors that can produce such data, as well as smart methods to process the gathered information. That's where signal processing comes into play. Signal processing is about analyzing data and making decisions. To provide very detailed maps of the area surrounding a vehicle, autonomous cars utilize LiDAR or radar sensors. These LiDAR and radar sensors produce vast amounts of data that is then processed in real time. The challenge is in using this data to help the vehicle make decisions just as we would if we were behind the wheel, if not better. Humans understand red means stop and green means go. We recognize and understand a yield sign. We know to pull over if we see and hear police sirens. We understand the context surrounding driving. Autonomous vehicles have to learn these rules, but they also have to learn the skill of prediction, critical for preventing accidents and for smooth and seamless autonomous driving. As humans drive, we predict what drivers and pedestrians are going to do next. We constantly assess the risks and hazards and try to minimize accidents. An autonomous car must do the same. Autonomous cars need to merge multiple types of data from many sensors that allow for fast object recognition, as well as develop the reasoning that translates data and object recognition into contextual understanding from which decisions can be made. Predicting the behavior of other drivers, bicyclists, pedestrians, and hazards should be integrated into decision-making. The promise and success of autonomous vehicles is tied to being able to analyze many data types, more than we have as drivers, to yield better decisions. Signal processing engineers provide these methods to autonomous vehicles. All of our driving decisions are done individually, but with autonomous vehicles, the decisions being made can be distributed and coordinated. It's possible that someday cars and even the road will be able to share data with each other. Road sensors could tell your car there are icy conditions ahead, so it automatically adjusts the way it drives to have smarter and better road traction. It's even possible that fleets of vehicles could coordinate the distances between each other automatically to optimize traffic flow, reduce fuel consumption, and lessen the risk of car accidents. We've come far and have even farther to go, but with signal processing engineers behind the wheel, we can visualize a not-so-distant future when we'll all be letting our cars do the driving. Will you accelerate us into the future of driverless cars? Learn more at signalprocessingsociety.org.
Okay. So after we talked about single channel signal enhancement in the frequency domain, we want to extend that to multi-channel signal enhancement in the frequency domain. So we start with signal model, problem formulation, linear filtering in the Fourier transform domain, performance measures, optimal filters, and then also with implementation with the short-time Fourier transform. Okay. Just like similar what we did with single channel, we do it with multi-channel. So it's an extension of the single channel. Okay, so the multi-channel, we have multi-channel, so we have more than a single sensor. And the signal model in the time domain is convolution between the desired source and impulse response from the desired source to the sensor M. So this we call it or denote it as xm. This is the desired signal part in the sensor number m plus noise. And as we defined it in the time domain, this part we try to estimate. So we need to choose the reference sensor. Which one is the reference sensor? Usually we would like to choose the best sensor. If we don't know, we arbitrarily choose one of the sensors. We hope that this one will be the best, or at least not too bad compared to the others. Once we choose, we try to estimate the signal in the reference sensor using the measurements, the noisy measurements from all sensors. And again, also here, we don't try to do the reverberation. So we estimate x1t, not xt, not the desired source, but the desired source as it is measured in the reference sensor. Okay? So now we apply Fourier transform to this model. So after Fourier transform, we have this one. Okay? So for each sensor, we have ymf. The convolution becomes a multiplication, so we get this desired part plus noise in that sensor. Okay? So of course we don't know this impulse response. If we know it, then we can try to do deconvolution, or in the frequency domain to try to divide or to do the inverse de-reverberation or de-blurring or whatever using this filter. So we can try to divide it by this filter and try to make it robust inverse so that we don't amplify the noise. This is a standard way. Okay. So our objective is to estimate x1f from the from the frequencies, and for simplicity, as we did with the single channel, we don't use the correlations between different frequencies, even though it's possible. If you have a way to estimate correlations between different frequencies regarding the desired source and the noise, and you have a reliable way to estimate them, you can use them. So it will add, if it adds reliable information, you will get better performance. But here, for simplicity, we don't try to estimate because we say maybe we don't know, or maybe it's difficult to estimate, maybe change in time, and so on. And so we simplify things. But of course, you can extend. You can make things, whatever information that you can get, reliable information, you can change your model and add this and try to find solutions or derivations that will use this additional reliable information. And generally, it will improve the performance. If it doesn't improve the performance, it means either that your information is unreliable or you didn't use it correctly. Okay? So here, if we ignore the correlations between different frequencies, we try to estimate x1f to obtain an estimate of this. So zf will be the output of the estimator. It will be an estimate of x1f. This is a scalar. Using all sensors noisy measurements from the same frequencies. So I goes from I to n. So it's a vector. So we can take this as a vector. So we can define a vector yf that contains, for the same frequency f, y1 up to ym. So it's the frequency component the same frequency component from all the sensors. And then we try to find an estimate of x1 using a filter. So if this is a vector, we can define a vector h such that we apply it. Let's transpose conjugate. We can define it in such a way, for example, something like this. If we multiply it with yf, we get an estimate of x1. So this is a linear filter. So suppose that you had more information about the correlation between different frequencies. What would you do? So instead of this vector, what would you do? Okay, if you have more information about the relation. So I extend. Exactly. So for each sensor, a sensor M or I here, it doesn't really matter. I can take all the frequencies, and then I can concatenate all frequencies for the first sensor, the second sensor, so on. So I will get here a longer vector, and here I will get a longer filter. This is one way to extend it, taking into account correlation between frequencies. Here, I estimate one frequency, f. Maybe, if I use the correlations between frequencies, maybe I want to estimate all frequencies at the same time of x1. Okay? Not single frequency. So what will I do? Here, instead of a vector, filter vector, I will get matrix, filtering matrix. Okay? So the filtering matrix will include and will derive estimation of all frequencies using this matrix. And I can find the optimal filtering matrix for different performance measures. You see, so everything that we learned, you can combine things. I don't teach you everything. You know, sometimes undergraduate students, whatever you teach them, this is what they know, and then you give them an exam based on what they studied. But when you become more mature as an engineer, you don't know only what you learned. You know how to combine things. So you know more than what you learned. Because you can always teach yourself beyond things. You can extend things yourself. So you can combine whatever we studied, you can combine the filters, the methods, the models into more. You can also extend linear method to non-linear method, and so on. You can combine things. Don't just know or learn whatever you learned, this is what you know. You want always to develop your knowledge, to combine things. And if somebody else didn't combine these things, you can take whatever you learned and combined, and you added additional knowledge, so you can communicate this with the community. Conference paper, journal paper, whatever. And you look in the literature. Okay, so sometimes you have questions. Suppose that this, suppose that this, what happens? And you ask questions, and then you look in the literature. Maybe somebody has some question. It doesn't mean that this is the only answer. Okay, so you can find different ways to do it, and you ask questions. So you always try every day, okay, all the time. You try to learn new things, and derive new methods, and so on. So you make an advancement in your area, and you don't feel like it's something you work on. It's more like something you explore, okay? So if something that you work, you feel, okay, I finished now. Now I worked until 6 o'clock. Now I don't think about this, because maybe it means that it doesn't interest you. If something interests you, you think about it all the time, okay? Because it's interesting, okay? And then there are ways to develop new things, and you enjoy. You enjoy from the knowledge, the additional knowledge. So here we gave an example of how to extend it. So this is the simplest way to do multi-channel linear filtering in the frequency domain. So it's the simple way. So when you study something, start with the simplest way. Don't go to the most complicated problem from the beginning, because it's more difficult to get intuition, okay? But you know that we can go further using the other method. So this is the simplest way to take advantage the spatial information. What is the spatial information? It means that we have sensors, different sensors, one, Y1T, Y, okay, and so on. So in the frequency domain, for a certain frequency, we have Y1F, and so on until YMF. So the relations between two measurements in the frequency domain give us some information about the signal, where it comes from, what happens, what are the reflections, and so on. So from this information, this spatial information, we can obtain a better estimate compared to a single sensor. So the improvement of using multiple channels, multiple sensors compared to a single sensor, this is the array gain. So array gain in signal-to-noise ratio. We can also get improvement of other performance measures compared to a single sensor. We always ask ourselves, when we add sensors, what is the gain? Because it adds more hardware, more sensors, more A to D or whatever, more hardware, more computational complexity. And we need to see if it's justified. What is the improvement in performance? Okay, so here we define this vector, y, as it contains, for frequency f, the measurements from all sensors. Also, we define x. So x is this measurement of the desired signal. So we see we can write it as xf multiplied with the vector g. G is the transfer function. Is the transfer function from the desired source to each of the sensors. G1 is the transfer function from the desired source to sensor number 1 in frequency f. Okay, so I don't repeat the dependence on frequency, because here we work on a certain frequency. Okay? So G1 is the transfer function from the desired source to sensor number 1, G2 is the transfer function to sensor number 2, and so on. So we have m generally different transfer functions. What happens if we don't have reflections? Free field, far field. What do you think? These transfer functions are the same or different? So what? So only phase, right. If it's in the far field, only phase. If it's in the near field, we have amplitude and phase. Okay, so if there is a desired source in the far field, the transfer functions from the desired source to each of the sensor, the difference will be phased only. So this is the model. So it's very useful to work with relative transfer functions. So relative transfer functions, we take the vector g, and we divide each element in the vector g with g1. So you see, we have the relative transfer function with regard to the transfer function from the desired source to sensor number 1. Because once we choose the reference sensor, this relative transfer function it provides us with information about the direction. And the thing is, why do we use relative transfer function instead of transfer function? Why do you think? Okay, so if I go to the previous slide, you see what is nice? I can write y as a function of x. X is the desired source in the origin. Suppose that here we have a desired source. This is xf, desired source. So instead of writing yf, or we call it lower, okay, so we can denote it with lowercase y. So we can write it as g. See, this is a vector. We can g vector multiplied with a scalar x, which is the frequency f of the desired source. Or we can write it as a function like this, x1, which is the desired signal, desired source signal that is received in the reference sensor, multiplied with the vector d. So the difference between g and d is that we normalize or divide it by g1. So what is the advantage of working here compared to working here? Okay, mathematically it's obvious, right? We just write it as multiplication with x, but here we write it multiplication with x1. So what is the advantage? So I want to mention two advantages. Let's think, what is the advantage? See that whenever we use a model, signal model, how it's received, we want to explicitly write it as a function of what we want to estimate. Okay? Makes sense. So we prefer to use this formulation than this formulation because we want to estimate the desired signal in the reference sensor. So it makes sense to write it like this. This is one advantage. Another advantage, another reason that we want to write it like that. You see, G is the transfer function from the source to each of the sensors. D is the relative transfer function. So what I suggest is we don't know G. Maybe we don't know G. So G is difficult to obtain from the measurements, from Y. It's difficult to obtain G from the measurement. But D we can obtain from the measurement. So it's quite useful to write the measurement as a function of D, the vector D multiplied with x1 plus noise. Okay? So you understand these two advantages. So it's a better way. When we write the model, we write it as a function of what we want to estimate, and also using information that we can obtain from the noisy measurements or from other things. But here, we can obtain D, and it's very difficult to obtain G, you see? How can we obtain D? We will see soon in the next slide how we can obtain D in a practical way. But the definition of D is simply taking G, G1, G2, and divide each element with G1. So this is the definition of D. And actually, D replaces it, gives us some information about the direction of the desired source. That's why many times we call it steering vector, because it gives us what is the direction of the source, where it comes from, direction of arrival. So it's a steering vector. Sometimes we call it propagation vector. Okay, this vector. Now, what we can see, that the vector, each element in the vector D, the relative transfer function, can be obtained actually from the correlation between signals in two different senses. So if we want to obtain the correlation between the relative transfer function G2 divided by G1, we obtain it using the correlation between X2 and X1. So we can write in a general way that the desired signal in the sensor number M, we can write it as, you see, of course, we can write it as multiplied. I will write it like this. Do you agree that XM F equals to GM F divided by X by G1? Multiplied with X1F. Okay? From the model. So here, what we see, this is the element. The element here, the relative transfer function, in the steering vector, D. So this relative transfer function actually is the same as the partially coherence between these two elements. I will show it. First, I will define what is this term. I will define it. What is the partially coherence between two terms in the Fourier transform? And then I will show how to obtain it. Okay, so first the definition. The partially normalized coherence function between two elements, two scalars, two complex scalars, is defined like that. So it's the expectation of the correlation between X1 and the XM complex conjugate, normalized by the variance of X1. So this is a definition, okay? And if I actually put here XM the way it is defined, the way according to our model, I get that this correlation partially normalized coherence function equals to the complex conjugate of this transfer function, relative transfer function. So that's why I can write here a vector. Instead that it contains the relative transfer functions, I can put the vector, which is vector of partially normalized coherence function with regard to the desired source. And the correlation is between X1 and the vector X. Here is the X1 and element of the desired source, XM. So here we get the vector, the coherence function between X1 and X. If it's not clear, I can repeat some of the material. Okay, so if you have questions. And the nice thing is here that we can actually, in many cases, we can estimate it from the data. How do we do it? Suppose that I have some intervals without noise, some data without noise, which means that I have X1 and XM. So do you agree that I can compute this expectation based on clean data? and we can normalize it. So I can obtain this value. It's a complex number, right? I can obtain this relative transfer function from data as long as I have some intervals with clean data. And suppose that the sensor array doesn't move in space, remains the same, and the source doesn't move in space. So everything is the same. So the relative transfer function, or this coherence function, will remain the same because there is no movement, change in space. Which means that afterwards, when I make new measurements with noisy data, I can use this coherence function or the steering vector. Okay? So I can estimate the steering vector or coherence function from clean data and then use it afterwards to apply it with noisy data. If the configuration in space doesn't change, which means that the source comes from the same direction and the array it's in the same position. It doesn't move. If it moves, I need to update. But this is a big advantage because, you see, if I try to find an estimate of the transfer functions, it's much more difficult because I need to know the source signal and so on. So it's more difficult. But the relative transfer function, I can use it from the sensors. So it's much easier. So it's useful in practice. Now, after I define the problem like this, you see, so I can define the problem like this, and I assume that I know the coherence function, or generally I will call it the steering vector. So if I know this steering vector, you see, so this is a vector that contains all measurements for the frequency f from all the sensors. This is a vector of length m. This is also a vector of length m. x1 is a scalar of, see, it's a complex scalar because it contains only the frequency component f for the reference sensor. And v is also a vector of length m. So this is our model, and we assume that we know the steering vector, which is the relative transfer function. Now we want to estimate a scalar x1 from a vector of length m. When did we do that? When did we learn how to estimate a single component, a scalar, from a vector, using a vector filter, linear filter? It's similar to what we did, single channel in the time domain. The only difference is with the single channel in the time domain, everything was real. Here, it's complex. But it's similar to what we studied in the, okay? So we tried in the single channel time domain to estimate a sample, xt, from a vector of L measurements, L noisy measurements. So here, we try to find a single component from a vector of M measurements. So it's similar in that sense, but it's not the same, okay? Because here we need to define different things. The performance measures will be defined differently. We have narrowband and broadband performance measures, just like we had for the single channel frequency domain. So we have different definitions of performance measures. And because of that, we will also have different filters in the Fourier, in the multi-channel Fourier domain. Okay? So there are some similarities, but many other differences. Okay? Definitions, terms, and so on are different. Okay. We discussed this. Now, we discussed the signal model in the Fourier transform domain. So we wrote that, if we go back here, okay, so we wrote that the vector YF, this is the vector of M samples. We wrote it as a vector D, or the complex conjugate coherence function between x1 and x, multiplied with the scalar x1f plus v. Now, the noise generally is composed of directional sources and other sources. So also we can write this background noise, we can split it into two terms. One term is noise terms that are coherent, and other terms which are incoherent with the noise in the reference sensor. So we can write V M. This is the noise component in the sensor M. So if we can write it, we can split it into two terms. One term which is correlated with the noise in the first sensor, and here the remaining noise. Okay? So it's a useful way because these two components are uncorrelated, which is nice. And here also, suppose that we have a directional noise source, so it will be contained here. And this will contain the remaining part. Not only thermal noise, but also some noise which is uncorrelated with the first noise. We can split it into two terms. So this part is the part that correlates with the noise in the first sensor. This part is uncorrelated. We can always do something split like that. Okay? And then we also have here the coherence function between V1 and Vn. We can always do something like that. So we can write the vector V, the vector that contains the noise for frequency f, using a vector, the coherence function between V, the noise, and the noise in the first sensor, in the reference sensor, multiplied by V1, plus remaining noise. So you see also this coherence function, we can estimate its correlation. Under which conditions can we estimate them? As long as the noise sources, at least the coherent noise sources, remain the same directions in space, if they don't move. If they move, I need to track this coherence function. And then updating the propagation vector or the steering vector, it's called tracking. When you have a moving source, you need to track its position. So you can do that. But suppose that its position in space is stationary, it stays the same. So this remains constant. And suppose that the noise also is stationary. So the variance of the noise remains the same, and so on. So I can estimate this coherence function, or the steering vector. It's the steering vector of the coherent noise. I can estimate it from intervals where I have only the noise without the desired source. And here I have the remaining part. So this part will be easier to handle. Why is it easier to handle or more easy to suppress? Because with multi-channel, I have the ability to filter out different directions. So I can do some spatial filtering in such a way that I have higher array gain for directions of the desired source, and low gain for undesired directions, for interferences. So this is like directional interference. And this is incoherent noise, which I can still remove by some ways or suppress. But usually, this I can reduce less efficiently using multi-channel sensor array. So this will may create more distortion. Maybe, depends. It's more like averaging uncorrelated noise in different sensors. So by averaging, I can reduce the variance of the noise, but it's very limited, the amount of noise that I can reduce such a way, or I need to use many sensors. Here, directional noise I can suppress by eliminating some directions that I would like to have low gain to that directions using sensor arrays. Okay? That's why it's useful to separate the noise into these two terms. Okay, to see, because if I see that here the dominant noise is in this part, then it's good. It means that I will be able to improve the performance without sacrificing too much distortion. If the significant noise is in this part, it means that the array is not that useful, and probably I need many, many sensors and then to average the signals and steering to the desired source and averaging. And then the reduction of this noise using array processing is limited. Of course, it's possible to do other post-filtering after the array processing. Okay. So eventually, so we write the measurements, the vector of measurement for the frequency f, as composed of three components. One component is the desired source. Second component is the coherent noise. Coherent noises are the noise that are coherent with the noise in the reference sensor. So and then the incoherent noise, incoherent components of the noise. So you see the incoherent noise is 0 in the first element. We have only the other elements, because in the first element, all the noise in the reference sensor is by definition coherent with the noise in the first element. So that's why we have 0 in the first element of the incoherent component, incoherent noise. Questions? So this is the signal model. This is a general signal model for multi-channel in the frequency domain. Multi-channel signal enhancement in the frequency domain. Okay. Now we compute the variance or the coherence metric or correlation matrix of the vector y. So the correlation matrix of the vector y, you see, because we work with complex numbers, so here in the time domain we put here transpose, here we have complex conjugate transpose, Hermitian transpose. Okay, so we have here transpose complex conjugate, and the expectation here, we see that it composed of three components from the previous equation. The first component is the variance of x1, the variance of the desired signal in the reference sensor, multiplied with a matrix. This is a matrix because this is a column vector, this is a row vector, so we have a matrix. So it's a matrix of the steering vector multiplied with the complex conjugate of the transpose of the steering matrix. So this matrix is a rank 1 matrix, see? Plus we have for the coherent noise component, the variance of the noise in the reference sensor, multiplied with a rank 1 matrix that is composed from the coherence function of the noise with the reference noise. And here it's a transpose. So this is also a rank 1 matrix, plus the correlation matrix of the remaining incoherent component of the noise. And this is the rank of this matrix is m minus 1. See, because we have 0 in the first component. So for the incoherent noise component, we have a rank of m minus 1. And what is nice is that these three components are mutually uncorrelated. So each one is uncorrelated to the other one. So we can work, so we have summation also after taking the correlation between them. So we don't have cross terms, correlation between them, because they cancel out. So if we define the input signal to noise ratio, what will be the input signal to noise ratio? Using this model, what is the input signal to noise ratio? This is the variance of the desired signal. See? In all the components. So what will be the variance? What will be the power of the desired signal? The input, for the input SNR. What is the input SNR? How is it defined? For multi-channel. See? So what we need, the input SNR for frequency F. So it's the narrow band input SNR. How is it defined? The SNR in the reference sensor. Okay? So it's phi x1 F divided by phi V1 F. Okay? So if you see here, this is the correlation, the variance of all components. So actually, in this matrix, if you take the first element will always be 1. Okay? And then you multiply with phi x1. So this is the power of the desired signal, the variance of the desired signal, and this is the variance of the noise. The first element in this matrix, the top left element, is 1. Okay, because it's always the correlation between V1 and V1 is normalized by V1, so it's 1. It's always 1. And here it's 0. Okay, so this input SNR will be phi x1 divided by phi V1. But also, if you take, you always, input SNR is compared to the reference sensor. So we know that it looks like that. The output SNR, we need to define. How do we obtain? So if we obtain it using a filter, we need to write it as the sum of the desired signal plus noise. And then we can check what is the variance, so we will get the output SNR. So linear filtering is just like I wrote over there. Okay, so by the way, this filter is for each frequency. Okay, so I need to add here F. Okay, because we work on each frequency separately. So the filter for each frequency is a vector of length m, for each frequency. It's not the same filter for all frequencies, of course. That's why it depends on the frequency. So we can write for linear filtering, we say linear filtering, the output of x1, an estimate of x1f is a superposition of the noisy measurement. So it looks like this. where this vector is defined as the gains that we give to each measurement in each sensor. So it's a vector of length m. Now I can write it, because I know that y, let's write it with the lowercase letter, so it will look like this, okay? So it's a vector like this. So I can write this as a summation of the component. Okay, the block diagram, it looks like that. So x1 plus y plus v1 equals to y1. And then this is the gain that we give to the reference sensor. And this is the gain that we give to any sensor, okay, or to all sensors. So here we have the gains. We take the summation, we get an estimate of x1, f, okay? So this is the block diagram of the model, summation, and also the gains in the frequency domain. So we have here that the estimate of x1 is h conjugate transpose multiplied with y, and we write y like this. So we have two components. One component is the filter desired, and one component is the residual noise. The filter desired is x1 f multiplied with h conjugate transpose steering vector or coherence function between x and x1, complex conjugate. Why did I move x1 to here? Because it's a scalar, okay? So I can move scalar to anywhere where I want. So this is the scalar, x1, and this is the vector, row vector, multiplied with a column vector. So this is also a scalar, okay? And this is, all this is scalar. But this is a vector, and this is a vector. And residual noise at the output of the filter is h complex transpose, apply h, complex transpose, multiplied with v, with the noise that is measured. So this is the residual noise. So if I ask you what is the output SNR, output SNR is the variance of X filter desired divided by the variance of residual noise. Okay? So the output SNR, narrowband, the narrowband output SNR will be the variance of X filter desired divided by the variance of the residual noise. Okay? So if I want to write the narrowband output SNR as a function of the filter, you see? So I can write it as phi x1 f multiplied with this number, magnitude squared. So it will be h complex or conjugate transpose multiplied with coherence function between x1 and x, magnitude squared. See, this is the variance of this part. Of h Instead of magnitude squared, I write it exactly, okay? So I'll take it as V okay? Like this. So this, I can write it as HF RV HF. Okay? You see? Or, sorry, instead of R, because we work in the frequency domain. So instead of R, we call it phi, okay? Because the correlation matrix in the frequency domain, we call it phi, okay? To make distinction between time domain and frequency domain. So it's a matrix phi VF, okay? This is the correlation matrix, like this. This is the variance of the residual noise at the output of the filter. And this is the variance of the filter desired at the output of the filter. So this ratio will give us the narrowband output SNR. Now suppose that I want to get filter with no distortion, like MVDR. So what should I require? So let's see what I have here. Okay, I go back. Here. You see, the output of the filter, we have two components. So this component, filter desired. See here, filter desired? If I want no distortion, like MVDR filter. So the filter desired should be what? X1, exactly. So X1. So the constraint or the requirement for MVDR, what will it be? Exactly. Okay. So we will require for MVDR, we will require the H, that H multiplied with gamma coherence function between X1 and X. We will require that this will be 1 for all frequencies. If it's 1 for all frequencies, what do we get? MVDR filter. So this will be the constraint when we derive the MVDR filter. If it's not satisfied, necessarily we will have some distortion. Okay? Questions? Continue. Okay, let's continue. So now we started already with the performance measures, but we can continue, okay? So with the performance measure. So we have the narrowband signal to noise ratio, just like we wrote before. And we can define the broadband input SNR, which is the summation or integral of the variance over all frequencies. So this is the power of the desired signal, the total power over all frequency. This is the total power of the noise, the variance of the noise over all frequencies. So this is the broadband input SNR. And you see that the input SNR is not an integral of the narrowband input SNR, of course. We have also the output SNR. The narrowband output SNR is the variance of the narrowband power of the desired signal at the output of the filter divided by the narrowband variance of the residual noise at the output of the filter. So this ratio, we had it before. You see, it looks like this. Now question. If we have MVDR, what will be the output, the gain in SNR? Okay. So if we have MVDR, okay. So if we have MVDR, we have this, which is the same. You see, D, the steering vector, is this steering vector. So here, the output SNR for MVDR we can write it the narrowband output SNR for MVDR will be phi x1 divided by H phi V H, okay? So if I take the gain in an SNR, the narrowband gain, which is the output SNR, the output narrowband SNR divided by the input narrowband input SNR, so it will be this divided by phi x and phi1. So we can write it as H F gamma V H minus 1, where gamma is the normalized correlation matrix. Okay, so gamma V will be the normalized matrix, correlation matrix of the noise. Okay? Okay? So, of course, with MVDR is the put no distortion, so the amount of gain in SNR is limited. If you want to increase the output SNR beyond that, you will introduce some distortion. Because MVDR, it says, don't touch the signal subspace. We remove the noise only from components or frequencies that contain no signal. So the gain in SNR is limited. But this is the gain in SNR that we can obtain using the MVDR. And also you can compute it for this is for the narrowband, you can compute it also for the broadband when we reach the MVDR. Okay, so the broadband output SNR is the integral of the total power of desired signal in the output filter divided by the total power of the noise, the residual noise in the output filter. And of course, also for the output SNR, the broadband, we don't have that it's an integral of the narrowband output SNR. It's different. Okay, so this is what it's possible to show. Okay, this is what I discussed. Okay, so the output SNR is smaller than a certain value, like this. If I want to discuss it, I can skip that because I just wanted to say that using the MVDR, it's the least amount of output SNR. So usually you can get higher output SNR if you introduce more noise. So this is the output SNR that is obtained using the NVIDIA, and then we can continue. Or if we take a filter like this, of course, filter like this, it means that we don't do anything. So this is no distortion, but we don't do anything. So that's why the output SNR will be as the input SNR. This is without any filter. This is obvious. Noise reduction factor. So the same way that we define noise reduction factor for time domain and single channel frequency domain and so on, the noise reduction factor, we can define narrowband noise reduction and broadband noise reduction factor. So the broadband noise reduction factor is the integral or the summation of the power of the noise in the reference sensor divided by the total power of noise at the output of the filter, which is the total power of the residual noise. This ratio, and we want to have it to be as large as possible. And also we can define for the narrowband for each frequency separately. See? So we have this. Desired signal reduction factor. So the broadband and narrowband. The broadband is the total power of the desired signal at the output, at the reference sensor. And this is the total power of the desired signal at the output of the filter. If we have the narrowband, so the narrowband is without the integral, so phi, the variance of x1, cancel out, and we have this. So you see, for MVDR, for example, what will be the desired signal reduction factor? The narrowband. What will be the narrowband? First, I'm talking about the narrowband. What will be the narrowband desired signal reduction factor for MVDR? 1, which means that there is no desired signal reduction factor. Of course, it should be 1, always. With NVIDIA, we have no distortion, so the desired signal reduction factor is 1. No reduction. And the broadband, if we put here 1, you see for each frequency, it's 1. So also, the broadband desired signal reduction factor is 1. We see from the formula or from the definition. But of course, for NVIDIA, we don't have any distortion. So it's okay, but as expected. And also for the noise reduction factor and the desired signal reduction factor, the broadband definitions are not integral of the narrowband definitions, the counterparts. And this is the constraint or the requirement that we put for the MVDR. This is the constraint that this number, you see that this number will be constant 1 for all frequencies. So when we reach to distortionless constraint, this is the constraint for the MVDR or other filters that we have with the requirement of distortionless constraint. And we have similar relations like we had for the other domains, that the gain in SNR, either for the narrowband or for the broadband, it's the ratio between the noise reduction factor and the desired signal reduction factor. Let's define the desired signal distortion index. So what is the desired signal distortion index? It means what is the mean squared error of the difference between the desired signal. You see here, it equals to X filter desired plus V residual noise. So if we take the difference between this and X1, take this error and we normalize it, we get the distortion index. You see? So this looks like this. Here, let's see the narrowband first. So the narrowband, X filter desired minus x1 magnitude squared expectation. So this is the variance of the error. The mean squared error of the distortion normalized with the variance of x1. We obtain this expression. So this is the distortion index, the narrowband distortion index. If we compute the broadband desired signal distortion index, so we have the integral here, the integral of the error. We sum the error over all frequency. And also here we have the integral in the denominator. And actually you see that this is a number, so we get here, we get the distortion index is the integral of the narrowband distortion index. Is a weighted sum, is a linear superposition of the distortion in each frequency of the narrowband. Based on the weight is the variance of x1, okay? Of course, because if in each frequency we have distortion, so the total distortion will depend on the strength of the signal in each frequency. So if I have distortion index, it's normalized, okay? It's normalized. If I have some distortion in some components of the signal, like percentage, it's normalized between 0 and 1. And so 10% distortion in strong components is much more significant than 10% distortion in weak signal components, okay? So the broadband distortion index is the summation of the narrowband distortion index multiplied with the variance of the signal. From this definition, you see it. But it makes also sense, because when you want to compute the normalized distortion index, it's normalized, yes? You give more weight to distortion where the signal is strong. That's why when you want to minimize the broadband distortion, you will try to minimize the broadband distortion by minimizing the narrowband distortion in the strong components. Because the strong components where the variance of x1 is large, it will induce much more distortion on the broadband, in the broadband. In the weak component, we can allow more distortion. That's why when we suppress noise, or when we want to control the trade-off between noise reduction and signal distortion, we allow distortion in the weak signal components. Because over there, the effect of broadband signal distortion is less significant in the weak signal components. Any questions? Okay. And of course, for MVDR, obviously, also the narrowband distortion is 0, and the broadband distortion is also 0. We don't have any distortion from this distortionless constraint. If we satisfy this distortionless constraint, we don't have distortion. No narrowband, no broadband. Using you see the definitions here. This will be 0. This will be 0, so the broadband also is 0. No distortion. Mean squared error. So mean squared error is the error between the estimate of x1 and x1. The mean squared error of this difference. So this difference is composed if we take this difference, it's composed of, can be split into two components, which are uncorrelated. One component is the error between the filter desired and X1, so that it relates to the distortion. And the other component is related to the residual noise. So if we take the mean squared error, so we have that the mean squared error, we can find explicit expression of the mean squared error as a function of everything that we know and as a function of the filtering vector. By the way, when we compare multi-channel filtering in the frequency domain using this model, you see that we do it for each frequency independently. So the length of this, you see the length of this filter. What is the length? M, exactly. The number of sensors, which is much smaller than the length of the filter in the time domain for multi-channel. What was there? ML, okay? And even we worked with matrices, so the filtering matrix was L by ML if we try to estimate L samples at a time. But even if we try to estimate a single sample of the time domain signal at a time, we have a very long filter of length ML. And usually, L is quite large in the time domain compared to M. M, we use a few sensors. M is usually a few, maybe 2, 3, 10. Sometimes people use like 100 sensors. But usually it's around 10 sensors, up to 10 sensors, sometimes even less. But in the time domain, L is usually, can be very large, depending on the correlation between samples. What's happened? Okay. So this is the mean squared error. And then we can, because we have explicit expression as a function of the filter vector for each frequency, which here is, so it's easier to work with, and everything else is known. So we can find derivative of this narrowband MSC with regard to the filter, and then we can find the Wiener filter. And because we work on each frequency separately, it's much easier to derive, okay? We will see afterwards. But here, this is the narrowband MSC, and it can be written as the summation of two components. One is MSC that is related to the distortion, and one MSC which is related to the noise. And we can also define the broadband. Okay, so we have explicit expressions, and we can define the broadband MSC as the integral of the narrowband mean squared errors. Between it will give, because it will give us the total mean squared error over all frequencies. You see that this relation that the broadband is integral of narrowband, it's only for the MSC. For the other performance measures, it's not. So don't confuse when you take broadband performance measure, it's not an integral or summation of all the performance measures in narrowband, in frequencies. It's not the total. Only for the MSC, it's like that. Even for the distortion index, it's not like that. It was a weighted sum. So generally, you need to verify if this relation. And why we are interested in the broadband? Because usually these are the performance measures that if we work with broadband signals, then we want to verify, we optimize the performance for the broadband performance measures. Okay? And we have certain different relations between both the narrowband and broadband performance measures. So even for the broadband performance measures, we have relation between the ratio between the MSE-based distortion and the MSE-based residual noise related to the other broadband measures, which is easy to verify. Now, after we defined the performance measures, we can move on to find optimal filters. So let's start with the maximum SNR. So maximum SNR, we wrote it somewhere before, but maybe it's not there anymore. Okay, so this is the output SNR for the MVDR. But generally, the output SNR, we saw that it looks like this here, this formula. Okay? So this is what we obtained here, which is the same. But it's nice to write it this way instead of magnitude squared. See? Why? Because here we have a matrix, and here we have a matrix. This is a scalar, a real number. And we have a ratio like this. So whenever we have a ratio of H and a matrix, let's call this matrix A, divided by H matrix B of this ratio, okay? So whenever we have a something ratio like this, if we want to find maximum of this ratio over H, so we know the solution. The solution will be proportional to the first eigenvector of B minus 1A. So the first eigenvector of this, so H is proportional to this first eigenvector of this matrix. By the way, if you are not familiar with that, it's a nice exercise to prove it, okay? By the way, if you're looking for also a nice proof, which is like a few lines of proof, it's in one of the textbooks of Van Tree. There is Optimum Array Signal Processing by Van Tree. It's a very thick book. So over there, there is also a few lines of the solution. Or you can check out in, maybe it's also in my book, in one of the problems. So there is also a proof of that. Okay, so we see that it's known that it's a maximized. So if we take this minus 1, see, minus 1, multiply with this matrix. So it will be the first eigenvector, but we know that this matrix is rank 1, okay? So if we take the maximum eigenvector, it means the eigenvector that corresponds to the eigenvalue, the largest eigenvalue of this matrix, then any filter that is proportional to this eigenvector will generate the output SNR. So actually we can write it, if we take the largest eigenvalue, we denote it by lambda 1, the largest eigenvalue of this matrix, okay, the largest eigenvalue of this matrix. We call it lambda 1. And of course, lambda 1f. Everything is a function of f because we work for each f, for each frequency independently. So first we see that lambda 1 is can be formulated like this. How do we do it? Because lambda 1 is the trace of this matrix. How do we know that lambda 1 is the trace of this matrix? So this matrix, you see, the rank of this matrix is 1. So if we multiply rank 1 matrix with another matrix, we get rank 1 matrix. And you know, if the rank, the trace of any matrix is the summation of the eigenvalues. Okay? So if we have only one eigenvalue, the remaining eigenvalues are 0 because it's a rank 1 matrix. So the trace of this matrix equals to the eigenvalue because we have only one eigenvalue. So the trace of this matrix is the eigenvalue, the only eigenvalue that we have, which is the largest because we have only one eigenvalue. So how we compute this trace? And you know, if you take two matrices, A, B, the trace of AB is the same as BA, the trace of BA. We can change the order. So the trace of this matrix, we can take gamma transpose and put it from the left. So we can change the order. So if we put gamma transpose from the left, we don't need to keep the trace anymore because this is a scalar. So we got an expression from of the eigenvalue. Okay, so it's very nice to see how we can find expression for the eigenvalue of that. So this is actually the eigenvalue. So this is the maximum that output SNR that can be achieved. So this is the upper limit for the output SNR using any filter, or the output SNR that can be achieved using the filter that maximizes the output SNR. Using here things that we know. You see, we know these terms. And actually, what I want you to try to understand how this expression, how it relates to the maximum SNR that can be achieved. So when you get a mathematical expression, don't move on. Try to see what does it mean. Okay? So what does it mean, this expression? Because it's very nice to look at this expression. First, we see that it's proportional to variance of x1. Okay, nice. Nice that we have here variance of x1. By the way, we can take the correlation matrix of the noise and we can normalize it. So it will be variance of x1 divided by variance of v1. And here will be normalized correlation matrix. So of course the output SNR that can be achieved is proportional to the input SNR. It makes sense, right? Because the higher input SNR, the higher is the output SNR. It doesn't mean that the gain in SNR is higher. Usually, for higher input SNR, the gain in SNR will be probably smaller. Okay? But the output SNR is proportional to the input SNR, which makes sense. More input SNR, you have higher output SNR. So what I want you to look at this value, the value of this scalar. What does it mean? What does it mean? This vector, what is this vector? It's like the steering. We talked about overview of multi-channel. So it's just like steering. So this value says that when we steer the observed signal, so we look for signal, the desired signal, it comes from this direction, right? It comes from this direction. So when we look to the direction of the desired source, we see how much noise comes from that direction. You see, so this gives us the amount of noise that comes from looking to the desired source direction. So the output SNR depends on two terms. One is the input SNR, because this we can normalize with the variance of B, so the input SNR. Second is how much noise comes from the direction when we steer it, when we look. So we steer the filter towards the desired direction. So this will give us the maximum amount of SNR. Okay? Questions? Okay, so I don't know if we have time. So we will continue. So actually, any filter that is proportional to this eigenvector, okay? So we have also any proportion that we can take here, any numbers, but these numbers can depend on the frequency because we do it for each frequency separately. So any arbitrary numbers which are different than 0, we will get maximum SNR because it will generate the output SNR, which equals to lambda 1, the first eigenvector. Okay, so we will continue with optimal filters in the multi-channel. So if something is not clear yet, you want to work more closely, if you have time, follow the problems at the end of each chapter. Try to solve a few problems, try to see, so you get more intuition, more understanding of the material. And of course, you can always ask me different things, but you can also derive things by yourself, some of the steps that I showed here. So we will continue with optimal filters, and also we will talk about implementation with the STFT. So today we talked about multi-channel in the time domain. So I want you now go back for the single channel and the multi-channel. See the differences of the filter as how we define these things. Also, multi-channel in the frequency domain compared to the single channel. Okay? And each example, if you have time, each example that I show, there are MATLAB code. MATLAB codes for all the figures. So you can also play with that. You can take different examples. And what I mentioned yesterday, the assignment that I gave last time with the single channel, with the speech, I hope you try to do that. And I gave you also the paper on speech enhancement, so you can play with that, and you can compare to what we did with Wiener filter, compare to more advanced method to do speech enhancement. So you have many things that you can add. It's up to you. Okay? So today, whoever celebrates Christmas, so Merry Christmas, enjoy the holiday. By the way, there is also Jewish holiday. Same time now, but usually they have different times, because Jewish holidays go according to the Jewish calendar. And it's different. But this year, there are Christmas and Hanukkah, which is the Jewish holiday this time. Usually they have some few days differences. But this year, it's the same time. So enjoy the holiday. And if you have other, I think in many countries, it doesn't really matter what is the religion. They have holiday during this time of December. I don't know why. So anyway, we say happy holidays, all the holidays. And even people who are not religious, happy holidays, because we celebrate all the time. So we will continue tomorrow. Tomorrow it's afternoon. Okay, so after lunch, we will continue here. So please take the time to rehearse as much as you can. Because during the course, it's better to understand. You understand the subtle differences if you rehearse and solve some problems. So I hope they don't come tired. Please don't come tired after lunch.